Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're diving into Lesson 7 of the Arduino UNO R4 Minima Ultimate Training Series, focusing on photoresistors, nested if, else if, and for loop statements. In this lesson, you'll learn how to build a light-activated LED sequence project with dependencies on the environment's lighting condition. In this project, all LEDs are expected to turn off if the environment is well lit. However, the LED sequence is activated when the photoresistor starts to sense a dimmer environment. At the end of the lesson, you'll perform a challenge activity implementing adjustable delay depending on how dim the environment is. When a certain threshold is met, the LED sequence gets faster as the environment gets dimmer. In addition, the number of LEDs being activated also increases under darker environment. So, if you want to learn how to build this project step by step from scratch, and in the process, you'll also learn how to use nested if, else if, and for loop statements, understand how photoresistors work and are implemented in circuits, then watch this lesson till the end. As always, before we start, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. SunFounder has kindly donated this Arduino UNO R4 Minima Ultimate Sensor Kit, which will be our constant companion throughout this series. So, if you're still searching for resources to help you in your journey to the new Arduino UNO R4, I recommend you give this one a look. This is available on the SunFounder website as well as on Amazon. The links are in the description below. So now, let's begin. For this session, you need the following materials: a photoresistor, also known as a Light-Dependent Resistor or LDR, and a 4.7 kilo ohm or 10 kilo ohm resistor. Or if you already have your SunFounder kit, you can simply use the photoresistor module. Here, there's no need for an additional 10 kilo ohm resistor since this module already includes several resistors and a potentiometer. You'll also need 8 LEDs with 8 1 kilo ohm current limiting resistors, a 100 ohm and 100 kilo ohm resistors, a breadboard, some connecting wires, and your Arduino UNO R4 Minima. In our previous lesson, you learned how to use a potentiometer as either a rheostat or as a voltage divider circuit. And using it as a voltage divider circuit, we can read its output voltage on Arduino using the analog read function. In this lesson, we can also apply the same principle to use a photoresistor in our Arduino project. To do that, first, we need to learn how photoresistors work. A photoresistor, also called a light-dependent resistor, is simply a variable resistor whose resistance varies depending on the light intensity it receives from its environment. The resistance of a photoresistor decreases as the light intensity it receives increases. In other words, it exhibits photoconductivity, an increase in the electrical conductivity of a material when exposed to light. Photoresistors are inexpensive and easy to use. That's why they are commonly found on many children's toys and other inexpensive products. They are also used for various projects such as adjusting the brightness of a device's screen or detecting day and night for automatic switching of solar street lights, camera light meters, and a lot more. If you have your multimeter, let's use it to measure a photoresistor's resistance as a function of light. In a well-lit environment, a photoresistor can have a resistance as low as a few hundred ohms. Here, I'm using a super bright LED flashlight directly against the photoresistor. Please note that each photoresistor performs differently from one another due to manufacturing and other factors. So, my readings here may slightly vary from yours. Now, in the dark environment, a photoresistor can have a resistance from several kilo ohms up to a few mega ohms. This is the electronic symbol of the photoresistor. It is a two-legged resistive sensor and it has no polarity, which means you can connect them in either direction in your circuits. Let's try to hook up this simple circuit diagram where we have an LED connected to a 1 kilo ohm current limiting resistor and a photoresistor in series. For this experiment, you will notice that as I block the photoresistor with my finger, the resistance increases. Thus, the LED gets dimmer. And as the photoresistor receives more light, its resistance decreases, and the LED gets brighter. Now, to use a photoresistor in Arduino, we can implement a voltage divider circuit. If you wish to review how the voltage divider circuit works, I provided the video links below. Here are the two wiring options when using photoresistors in a voltage divider circuit. On the left, the photoresistor is labeled as R1. As you can observe, the output voltage, Vout, increases as the light level it receives increases. Vout will also decrease as the light level decreases. Assuming that we have a suitable value for the fixed resistor R2 in series with the photoresistor, using 5 volts as Vin, we can make the output voltage of this circuit vary between a little over 0 and a little under 5 volts for a range of light intensity. As we've learned in Lesson 3 of this course, using Ohm's law, voltage is equal to current times resistance. We also know that the same current must flow to both resistors connected in series. So, we can substitute this current with the total voltage Vin over the total resistance, R1 plus R2. Thus, we have the output voltage Vout is equal to Vin multiplied by R2 divided by quantity R1 plus R2. On the right side circuit, the photoresistor in the voltage divider configuration is labeled as R2. Here, the output voltage increases as the light level it receives decreases. And the output voltage decreases as the light level it receives increases. Now, one question remains. How do we know what value to use for the fixed resistor? Well, we can use any resistor value depending on the lighting condition of the environment you want your project to be deployed. You just have to identify first your environment lighting levels of interest. For example, do you care more about a brighter environment or a darker environment to measure? Because ideally, you would want your output voltage to vary equally across the entire ADC range of 0 to 5 volts. To illustrate what I mean, I'll use the first circuit diagram on the left where the photoresistor is R1 and the fixed resistor is R2. Then, I'll be using a 100 kilo ohm resistor for the fixed resistor R2. Here, notice that in a well-lit environment, the output voltage varies only by a few millivolts. But in a darker environment, we can get a good range of values between 5 volts down to 0 volts. So, if you want more sensitivity to darker light levels, use a bigger fixed resistor value like 100 kilo ohms. On the other hand, if I use a smaller fixed resistor value like 100 ohms, we can get a good range of 0 to 5 volt values in a brighter environment. Our circuit becomes more sensitive to higher light levels. Now, for most circuit diagrams you'll see online, a fixed 10 kilo ohm resistor is commonly used, as it is a nice compromise to have a good balance between lighter and darker environments. So, to help you select a fixed resistor value depending on your working environment lighting condition, consider this Axel Benz formula used by Adafruit, where the fixed resistor is equal to the square root of the minimum photoresistance value multiplied by the maximum photoresistance value. For example, in my working environment, the minimum photoresistance value when I use a direct flashlight against the sensor is about 100 ohms. And the maximum photoresistance value when I place this cup over the sensor is about 100 kilo ohms. So, substituting these values would give me about 3 to 4 kilo ohms fixed resistor value. Here, I could use a 4.7 kilo ohm and it should give me a nice range of ADC values between 0 to 5 volts under this current lighting condition. To use this voltage divider circuit in Arduino, simply connect the output voltage to any of the 6 analog input pins A0 to A5. Similar to our last lesson, I'll use A0. Also, I'll be using a similar program from Lesson 6. Here, we define sensor pin A0, and then we initialize the serial communication. And in the loop function, we call the analog read function and store the return value to the variable ADC value of type int. We also computed for the equivalent analog voltage ranging from 0 to 5 volts. And finally, we print both the analog volts and the ADC value. I'll upload the code and test if it works. Here, you can clearly see that under a well-lit environment, the analog voltage it receives is a little above 4 volts. And it will continue to rise as I intensify the light. However, as the photoresistor receives less light, the voltage that our program receives gradually drops to a little above 0 volts. Please note that if you use the second circuit implementation, where the photoresistor is R2, the relationship would be inversed. That is, as the photoresistor receives less light, the voltage increases. And under a well-lit environment, the voltage decreases. So, it is your decision. Either way, you can easily adjust how the Arduino would respond programmatically. Now, if you have your SunFounder photoresistor module, the second circuit implementation presents a similar relationship regarding the photoresistance and the output voltage. This module also includes a built-in potentiometer that can be used to adjust the sensor's digital output threshold. Yup, you can use it as an analog or as a digital sensor. It has pin out of analog out, digital out, ground, and VCC. To test if it works, I'll remove this component first and rearrange these wires a bit. So I've arranged this as analog out, no connection, ground, and VCC. For now, I will not use the digital out of this sensor. Here, notice that as I block the light from the photoresistor, the voltage being received also increases. You'll also notice that as the voltage reaches above 2.5 volts, which is the current threshold, the digital output LED turns off. Otherwise, it turns on. In this module, you can adjust this threshold by tweaking this potentiometer. I'll rotate this slightly in a counterclockwise direction. Now, we can easily verify this as well in our serial monitor by connecting this digital output pin to the Arduino and modifying our program. So, I'll connect the D out of the sensor to pin 12 of the Arduino. Then, in our sketch, I'll define another constant D sensor pin at pin 12. I'll configure the pin mode to input. And inside the loop function, I'll declare a Boolean variable digital to hold the return value of this digital read function. And then, I'll duplicate this code to print the digital input of either 1 or 0. I'll upload the code and test the result. Here, we can clearly see that the digital input received is 0 when the analog input voltage is below 2 volts. And when it reaches a little above 2 volts, the digital input turns logic 1. Depending on your project, you can either use the analog output or the digital output pin or both pins of the photoresistor module and read them using the analog read and the digital read functions. So, to accomplish the LED sequence project that I have shown you earlier, consider this circuit diagram. Let's connect 8 LEDs to the Arduino's digital pins 0 to 7. Each has a 1 kilo ohm current limiting resistor. Now, in our sketch, we can define 8 constants or 8 variables signifying digital pins 0 to 7 and then configure them all as output. However, I'm not going to do that here. Instead, I'll introduce the concept of for loop. For loop is another looping statement used in C language, similar to the while loop we discussed in the previous lesson. However, in a for loop statement, the variable initialization, condition, and increment or decrement expressions are put in one place, inside these parentheses. Same with any looping statement, for loop statement is very useful when simplifying codes that need to be executed repeatedly. For example, instead of calling the pin mode function 8 times to set the mode of the digital pins 0, 1, 2, 3, 4, 5, 6, and 7, I can simply use this for loop statement and then initialize a variable, let's say pin, and set it to 0. The idea is to make this for loop statement to loop 8 times. And with each iteration, the value of this pin variable changes. It started with 0 and has to be incremented by 1 after every loop. So it is going to count from 0 to 7. And to achieve this, we could have a condition that checks if the pin variable is still less than 8. And if so, perform the statements inside the loop. And then loops back to perform the increment operation, which is to add 1 to the pin value. This for loop repeats continuously so long as the condition remains true. And once the condition becomes false, the for loop terminates and proceeds to the next statement after the loop. So inside the for loop code block, the statement that we want to execute 8 times is to call the pin mode function. Here, we need to specify the pin number. In this case, I'll use the pin variable so that each pin from 0 to 7 can be configured one by one as output. And that's it. Now, inside the loop function, I'll introduce how to use nested if conditions, meaning an if statement inside another if statement. This code structure is so common that you'll end up writing one yourself most often. You could also have a looping statement inside an if statement inside a looping statement, or a looping statement inside another looping statement, and so on. There's no limit to this. For example, we could have a simple if-else statement to check whether the digital sensor reading is high or low. If it reads high, meaning we reach a certain threshold signifying a darker environment, thus we could have a code that turns on all the 8 LEDs. So, inside this if block, instead of calling the digital write function 8 times, I'll maximize the use of the for loop statement to turn on all the LEDs one by one. Similar to the previous for loop implementation, I'll initialize the variable pin and set it to 0. Check if it is still less than 8. If it is true, then perform the statement inside this code block before looping back to increment the pin variable by 1. So, what we want to do inside this code block is to call the digital write function 8 times to turn on all the LEDs starting from pin 0 up to pin 7. On the other hand, if the sensor reads low, we'll turn off all the LEDs. So I'll simply copy this code and paste it here, and then change this to low. I'll upload the code and see if it works. And it works perfectly. Now, notice that you didn't see each LED turning on one by one. It looks like all of them turn on simultaneously. Well, we know that the loop execution is very fast, and if we want to see each LED turning on one after the other, we can put a short delay after every digital write. I'll upload the code and see what happens. And now, you can see each LED turning on one by one from pin 0 to pin 7. Although it works, there are some issues here that we are not going to answer for now. For example, Notice that once the for loop has started, even if I remove my finger blocking the light, it still needs to finish 8 loops including the delay. It doesn't automatically stop and turn off all the LEDs. Now, the use of nested if and else if statements become handy when you need to check for multiple possible conditions or outcomes aside from just two. For example, what if instead of just simply turning on all the LEDs when the sensor reads high, the number of LEDs turning on will depend on the range of the ADC values, and we have a wide range of values from 0 to 1023 instead of just one bit high or low. Say for example, if the ADC value received is less than or equal to 500, we only want to turn on 4 LEDs connected from pin 0 up to pin 3. If it is within the range of 501 up to 600, we turn on 5 LEDs from pin 0 up to pin number 4. If it is within the range of 601 up to 700, we turn on 6 LEDs up to pin 5. If it is within the range of 701 up to 800, we turn on 7 LEDs up to pin 6. And if it is above 800, we turn on all the LEDs up to pin 7. So, to implement this, we need to have another if statement inside this outer if statement. This is known as nested if statements. So, if the digital reading is high and the ADC value is less than or equal to 500, we will turn on 4 LEDs connected from pin 0 up to pin 3. So, how do we do it then? Well, there are several ways to accomplish this depending on your logic formulation. One idea here is to modify the condition inside this for loop. Instead of having a fixed value here of 8, in which case turns on all the LEDs, I'll replace this with a variable I'll call last pin and change the condition to less than or equal to last pin. So I'll declare this variable and initialize it to 0. Now, if this condition turns out to be true, we set the last pin value to 3. In effect, this for loop will only turn on 4 LEDs from pin 0 up to pin 3. Now, we can do the same for the rest of the other if conditions. However, instead of using multiple if statements in sequence, there is a more appropriate construct to use: the else if statement. First, you must know that the use of else if statement is optional. Second, you can have as many else if statements as you want. Third, the order of evaluation is sequential. If the first else if statement has been satisfied, meaning the condition is evaluated as true, then the rest of the remaining else if statements will no longer be evaluated. Unlike with multiple if statements in sequence, in which all if conditions will be evaluated regardless of the outcomes of the previous if statements. So, if the first if condition returns false, we could test for another condition using the else if statement. Else if ADC value greater than 500 and ADC value less than or equal to 600. Here, the double ampersand operator means logical AND. We have 3 logical operators used in C language: logical AND, logical OR, and logical NOT. When using a logical AND operator, for this entire condition to be evaluated as true, both conditions, left and right, must be evaluated as true. Otherwise, it will return false and will proceed to the next statement, which is going to be another else if block in this case. In simple words, if the ADC value is within the range of 501 up to 600, then set the last pin to 4. In effect, the for loop will turn on 5 LEDs from pin 0 up to pin 4. For the rest of the remaining conditions, I'll just duplicate this line of code 2 times and change the range 601 to 700 and set the last pin to 5, 701 to 800 and set the last pin to 6. Now, for the last one, instead of creating another else if statement with condition that checks for 801 and above, I'll simply use the else statement and set the last pin to 7. Now, I'll upload the code and see how it behaves. And as you can see, it works. But this is not similar to the one that I have shown you earlier. Notice that I still need to move my finger that is blocking the sensor for the LEDs to reset. What we want is to have a continuous LED sequence so long as the sensor is being blocked. A simple remedy is to copy this code that resets all pins to low and paste it here after turning on the LEDs. Now, instead of starting from 0, I'll reset starting from pin 1 so that pin 0 is always turned on. Let's try it one more time and see if it works. And as you can see, it works perfectly. When using photoresistors in your project, you must know some of its limitations. According to some studies, a photoresistor is most sensitive to light differences at lower lux levels, meaning in darker environments. Also, it has a noticeable response latency from a few milliseconds up to a second when used to measure rapid fluctuations of light. So, if you want to use a more accurate and responsive sensor, you might want to check phototransistors and photodiodes. For your challenge activity, I want you to improve this program by incorporating an adjustable delay depending on the environment's lighting condition. Similarly, maintain the previous condition that the number of LEDs being activated also increases as the photoresistor receives less light. Here, the delay changes depending on how dim the environment is. The delay gets faster as the environment gets dimmer. And the delay gets lower as the environment gets brighter. As a hint, you need to declare a delay variable and modify the nested if and else if statements to set the delay differently depending on the range of the ADC value. Again, thank you so much for joining me in this lesson, Understanding Photoresistors, Nested If, Else If, and For Loop Statements. For our next lesson, you'll learn how to control RGB full color LEDs through pulse width modulation. If you found this lesson enlightening, don't forget to hit the like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and keep in mind, education is life. See you in our next lesson. Happy coding!